to control system classes. The topic for today's discussion is PID controller. What is a PID controller? It will produce the output U of t in proportion to the error signal, integral of error signal and derivative of error signal. We can write U of t is proportional to E of t plus integral of E of t into dt plus d by dt of d by dt into E of t. To remove these proportional symbol, let us add a constant Kp for proportional controller, Kp by Pi for integral controller, Kp into Td for derivative controller, Kp into Td is called Kd and Kp by Ti is called integral gain constant Ki. Take Laplace transform on both sides and we will get the transfer function of PID controller as Kp plus Ki by S plus Kd by S. So whenever we took the log of with the transfer function, we can able to understand the controller used as PID controller. And what is the purpose of PID controller? It will improve the stability of the system and try to decrease the steady state error. To realize the proportional integral derivative controller using op-amp, we can use a two-stage controller. As it is an inverting operation amplifier, we require two stages. The second stage is called sign changer with equal value of resistance. The first circuit is called the combination of integrator and differentiator. As if we have a capacitor in a feedback, we understood it is an integrator. A capacitor in parallel with the input impedance, it is called as an differentiator. So both resistance are connected here, the capacitors are connected here in order to realize a proportional integral and derivative controller. And the needed terms are given here. What is the necessity to go? Let us check what will happen if we are using only a proportional controller. To the planned function g of x is equal to 1 divided by s square minus b, assuming the value of b is greater than 0. What happens if b is equal to 0? If b is equal to 0, the double poles will be located at the origin. Let us assume the poles are b value is greater than 0. So what will be where the poles are located? The open loop poles are located at s is equal to plus or minus root b. Right? So we have two equal and opposite poles. It means one pole will be present in LHS of value root B and another pole will be present in RHS with a value of root B. As when the poles are placed in the RHS, we know that the system will become unstable. So the original G of S function is unstable. So let us add a controller to make it to a stable. So we have added a proportional controller here of value Kp is greater than B. As we have the poles s square value is b is b minus kp. S square value is b minus kp. As kp is greater than b, always this value will be negative. As this value is negative, let us take the function as j. So x is equal to plus or minus j root of kp minus b. This is my closed loop poles and the closed loop poles are placed on the imaginary axis. So the system is marginally stable. But my objective is to make the system to become stable. But with adding a proportional controller, an unstable system is shifted to marginally stable system. This is the major possible thing we can do with the P controller. So let us change to the original system G of x. Let us add now proportional derivative controller and let us check what will happen now. So a proportional derivative controller Kp plus S into Kd is added here with again B value greater than 0. Let us write C of S by R of S for the given closed loop system, assuming Kp is greater than B, Kd is greater than B. So we have two values Kp and Kd. When it is adjusted, the system poles can be located anywhere on the system plane. So the poles are placed in order to make the system to be stable. Accordingly, the value of Kp is assumed to be greater than B and Kd is assumed to be greater than 0. Now let us calculate the final value of the system. The final value theorem is used here. So limit t tends to infinity C of t or in S domain limit S tends to 0 S into C of S. This is the formula usually we will use, but here to calculate the final value we have used here. So limit S tends to 0, the C of S function is substituted, R of S value is 1 by S. So when we substitute S as 0 in this equation, I am not getting my final value is 1. What is my final value for the given system R of S? R of S is 1 by S. It means it is a unit step signal. So unit step signal, my reference input is 1. So C of S need to be 1. But with derivative controller, the final value doesn't achieve the 1, but the system is stable. So the proportional derivative controller shifted the marginally stable system to a stable system, but still my controller has steady state error. So I want to reduce my steady state error. So I'm going to introduce a proportional integral derivative controller in the next stage. And in that case, we can understand that my error will become 0. So to the original function 1 divided by s square minus b, now a proportional integral derivative controller is added here. C of s by R of s for the respective blocks is reduced and it is given here. And again the same assumption, Kp is greater than b, Kd is greater than 0. Using again a final value theorem, when we substitute s as 0, I am getting my final value is 1. So my system is stable with proportional derivative controller. My system error, steady state error is 0 with PID controller. That is the reason we are going with PID controller and not with only PI, not with only PD controller, or not with any individual combinations of controller. Hope you understood about the importance of proportional integral and derivative controller. Let us cross check the same with the MATLAB results. So a MATLAB program is written with the 3 stages here. The first stage is without controller. My assumed planned function is 2 divided by s square plus s plus 2. Then I have assumed here the proportional controller is only introduced as a stage 1. Then I have, proportional integral controller is introduced in stage 1. Then I have introduced proportional integral derivative controller. What will be the changes? With proportional integral controller, we know that it will introduce as a 0. So it means an oscillation will be occur in the starting. The rise time will be reduced. But with introduction of PID controller, my damping factor is improved and hence my oscillations will be reduced with PID controller. Let us cross check the results with an output program, MATLAB output program. So this is a planned transfer function. I have written the closed loop function and you can check here. With the introduction of PI controller, my rise time get reduced. The 0 is added here. As the 0 is added with the proportional integral controller, my rise time is decreased. With proportional integral derivative controller, my rise time is further decreased. What is my settling time? What is my overshoot? Here overshoot is 30%. Here overshoot is 70%. Why overshoot is increased? Because of the introduction of zeros. 20s plus 10, the 0 was introduced. Here no 0 without controller. With controller, a 0 is introduced. So overshoot has increased. What about the overshoot with PID controller? Overshoot is 0. What is my settling time? My settling time value is not a number. Here the MATLAB results is given using the command step info. I have taken this. In my settling time is not a number. It means the time taken for the system to settle within 2% or 5% of error is settling time. So the MATLAB output doesn't reach 2% error. That's why it is given as not a number. So it means my system has increased slowly. It increases with sufficient time and without oscillations it reaches my final value. That is PID controller. The program is executed with these values of Kp, Ki and Kd. Let us see the waveform. This is without controller. With controller with adding zeros, with PI controller with adding zeros, initial overshoot occurs, then it reaches the final value. With PID controller, the oscillations in the transient portion are suppressed and it reaches the final value of 1 here. So this is the difference between PI versus PID. Let us cross check our concept with PD versus PID. What happened without PI controller? So initial portion is same without controller. Then a program is called, it is here you can observe C is equal to PID of Kp, 0, Kd. This command operates only a proportional derivative controller. Then the output is printed. Again, PID controller is called and the output is printed. Let us write the results here. So first is without controller, then the next one is PD controller. With proportional derivative controller, even in the previous slide we had discussed, there will be a steady state error. My final value without controller is 1. With introducing controller, it creates an error and hence my final value is 0.909. But With PD controller, we can observe my overshoot has decreased to 7.98%. Here initially 30%. But my rise time has decreased with the help of PD controller. But the steady state error still occurs. It persists. From the DC gain calculation, we can even understand what is DC gain. By substituting SS0, we can able to get the DC gain value. DC gain value is nothing but a final value of output. But I can observe I have a steady state error. To minimize this steady state error, I have added an integral controller of function with the Ki value as 5. Now I can understand that my rise time has a little change according to the values, but my overshoot has become 0 and my final value has become 1. This is a MATLAB results. I have used the command DC gain in the program. You can also cross check the results by substituting SS0 here. So what is the conclusion we can make here? With PD controller, I have a ESS steady state error. With PID controller, the steady state error is decreased. Now let us see the waveform. So this is without controller. With PD controller, the oscillations were suppressed, but I have an error. With PID controller, I don't have initial oscillations. The transient portion got improved and I got a perfect steady state response. So that is the purpose of PID controller. So what is the summary we can say? A PID controller take action on a transient portion as well as my transient portion as well as on steady state portion, and hence my steady state error is decreased or it becomes 0, and also my damping has very decreased. So I have a reduced rise time, I have reduced peak overshoot as well as I have achieved my desired value. That is the purpose of PID controller, and hence it is used in many projects to obtain the required output. Thanks for watching.